Hello, I will be discussing my work on non-commutative polynomial factorization via Higman linearization. It is joint work with V. Arvin. First, we recall basic definition of polynomial non-commutative polynomial ring and its basic properties. Let X be a set of variables x1 to xn. Then non-commutative polynomial ring is simply a collection of all finite f linear combinations of words over x. So this example gives a polynomial with three monomials and the respective coefficients. Since we are working with non-commutative setup, clearly variables do not commute. And the ring operations are naturally defined. Addition is component-wise and multiplication is usual convolutional product, which respects the ordering. Another standard fact is fx is an integral domain. That is, if we take product of two polynomials in fx and it is 0, then either of the polynomial must be 0. Now, a few more standard definitions. So, degree of polynomial is degree of its largest degree monomial, and degree of monomial is simply length of the monomial. And by non-trivial factorization of polynomial f, we simply mean an expression f equal to gh such that g and h have non-zero degree. And we call a polynomial f to be irreducible if it doesn't have any non-trivial factorization. So this polynomial x plus yz is clearly a degree 2 irreducible polynomial. Now, unlike commutative polynomial ring, the non-commutative ring is not a unique factorization domain. A standard example is a polynomial xyx plus x, which has two distinct factorizations, x times yx plus 1 and xy plus 1 times x. Now let's recall a few important algorithmic questions over the non-commutative polynomial ring. The first question is the polynomial identity testing problem, where a polynomial f is given as input in some standard representation, such as arithmetic circuit or arithmetic formula or algebraic branching program, and goal is to test if f is identically 0. So this problem is quite well studied. For the case of ABPs, there is well-known deterministic algorithm due to Raz and Spilka. And for case of arithmetic circuits, if the circuit computes polydegree polynomial, then there is an efficient randomized algorithm due to Bogdanov and V, which is based on Amitsur-Levitsky theorem. Another interesting problem over non-commutative ring is a factorization of a polynomial. So given a polynomial f in some representation as input, goal is to find all irreducible factors of f. And algorithm is supposed to output each of these factors in certain standard representation. Though this problem is quite natural, it hasn't been much investigated in the literature. In fact, in commutative setting, there is a close relation between complexities of these problems. And a work of Koperthy, Saraf, and Spilka gave a reduction from multivariate polynomial factorization to the polynomial identity testing problem modulo univariate polynomial factorization. In the current work, we come up with an efficient randomized algorithm for factorization of non-commutative polynomial given by arithmetic formula or in sparse representation. So let's recall some related work in commutative setting. So in commutative setting, factorization problem is quite well studied. The celebrated result of Kaltofen gives an efficient randomized algorithm for the problem where the input polynomial is accepted as arithmetic circuit and algorithm outputs arithmetic circuits for all irreducible factors of f. One thing to note is Kaltofen's algorithm can be seen as a randomized reduction from multivariate to univariate factorization. So multivariate to bivariate through Hilbert's irreducibility theorem and from bivariate to univariate via Hensel lifting technique. It is also known that Kaltofen's algorithm can work in black box case as well. It is work due to Kaltofen and Traeger. In non-commutative case, there is not no not much is known. So there is one of the work, our work with Gaurav Ratan, where we study the problem of factorization of polynomial if polynomial is either homogeneous or multilinear. In this case, we provide efficient algorithm. Our algorithm even works in black box case as well, and it works for either of the representation, arithmetic circuits or ABPs. Now, crucial thing to note is in both these cases, polynomial have unique factorization, and in fact, this uniqueness plays a crucial role in our algorithm. More in mathematical setting, this work due to Helton, Klepp, and Wolsik study the singularity locus of non-commutative polynomial f for algebraically closed fields. So by singularity locus, we mean a collection of all n tuples of matrices such that if we take determinant of evaluation of f on that matrix tuple, it vanishes. What they show is if f is irreducible polynomial, then for sufficiently large d, the hypersurface LD of f is irreducible. In fact, they obtain a relationship between factorization of f into irreducibles and decomposition of hypersurface LD of f into irreducible hypersurfaces. And this connection holds true for sufficiently large sized matrices D. Another related work I want to mention now, for which we need a simple definition. So we call a polynomial f to be commutatively non-zero if there exists some scalar substitution on which polynomial evaluates to a non-zero number. In the HKV18, an algorithm is sketched for factorizing such commutatively non-zero polynomials based on state space realization techniques, which involves computation of factorization of inverse of linear matrix L, which is obtained via Higman linearization. Unfortunately, this technique is crucially using the fact that the polynomial is commutatively non-zero, and we don't see any way to make this approach work for case of general polynomial which are possibly commutatively zero. Our work mainly relies on Cohn's theory of factorization. Cohn has systematically investigated the problem of factorization and in general the structure of free ideal rings. These rings can be thought of as generalization of principal ideal domains in non-commutative case. And this theory is quite general and includes the polynomial, non-commutative polynomial ring as a special case. So Cohn defines what he calls as weak algorithm, which is similar to Euclid's division algorithm, which he uses to study the structure of these rings. Our work is crucially based on some of the ideas from Cohn's theory. So most notably, the way Cohn uses the Higman linearization. So basic step in Cohn's work is first to transform given non-commutative polynomial f to a linear matrix. So by linear matrix, we mean a matrix whose entries are linear forms in the non-commuting variables. So once we do that, then the problem becomes amenable to the linear algebraic approach. So we describe next what is Higman linearization. So given a polynomial f, Higman linearization is basically a sequence of elementary row and column transformations, which we apply on this matrix f o plus id minus 1. So it is a matrix shown on the slide where top left entry is f and bottom right block is identity matrix. So using these elementary row and column operation, somehow we want to get rid of large degree terms in F and eventually make the matrix linear. So to see it more explicitly, let's consider a single step, rather the first step of Higman linearization process. So suppose we have a polynomial f plus g times h. we expand it into 2 cross 2 matrix by adding 0 below the polynomial and 0 towards right, and 1 at the diagonal position as shown on the slide. Now this we apply row operation and a column operation on this 2 cross 2 matrix as shown in the last equation, where the first operation is row operation in which we add g times the second row in first row, and second is the column operation in which we subtract second column times h from the first column. So we can see that the effect of these two operations is the term gh has vanished from the top left entry. But at the same time, these polynomials g and h are introduced at certain locations in the matrix, but clearly degree of g and h is strictly smaller than degree of gh. So this process, if we continue, eventually we can express f o plus id minus 1 as p times l times q, where the l is the final linear matrix obtained, p is the matrix obtained by combining all row operations, and q is the matrix obtained by combining all column operations. It is easy to see that p is upper triangular and it has all diagonal entries 1. Similarly, q is lower triangular with all diagonal entries 1, and both P and Q are invertible matrices. Now, as we have transformed the polynomial into linear matrix, we need to define notion of factorization as well as irreducibles in case of these matrices of polynomials. Most of these definitions are from Cohn, so we quickly recall some useful definitions. So first, a matrix M with polynomial entries, it's called as a full matrix if it is invertible in the skew field. So informally, skew field is essentially a field of fractions for non-commutative polynomial ring. It is not very easy to define because elements of skew field do not have canonical representation as ratios of two polynomials. But for the current purpose, it suffices to see this analogy. The full polynomial matrices are essentially analogous to full rank matrices in usual setting. Next useful definition is unit. So a unit is a polynomial matrix which is invertible in fx, and units plays the similar role as that of scalars in case of usual factorization. Now, a full non-unit matrix is called as an atom if it cannot be expressed as product of two full non-units. Clearly, atom is analogous to notion of irreducible polynomials. Another important concept we need to describe our algorithm is of common invariant subspaces of matrices. So let A0, A1, so on up to An be D cross D matrices over field F, and V is a subspace of F power D. It is called as an invariant subspace of these matrices if for every I, if we apply AI on any vector V in capital V, we get back a vector in capital V. So clearly 0 and F power D are trivial common invariant subspaces for any collection of D cross D matrices. One non-trivial example is in case of single matrix, if we look at a space spanned by any eigenvector of the matrix, it is non-trivial invariant subspace for the matrix. In general, for matrices A0 to An, they have a non-trivial common invariant subspace if and only if under some basis change, we can transform linear matrix L to the block form shown on the slide, which has 0 as top right block, and that block has non-trivial size, where L is the matrix obtained from A0 to N, simply sigma AIXI plus A naught. So this form is very crucial for our algorithm, and this problem can be solved efficiently in randomized polynomial time in case of finite fields. It is algorithm due to Ronai, which we need crucially for our algorithm. Now we describe broad steps of our algorithm. So first step is to transform F into a linear matrix L using Higman linearization process. We want to do it efficiently, and for that we use this result by Garg, Gurowitz, Oliveira, and Wigderson. So by efficiently doing Higman linearization, I mean given a polynomial f as a formula, we want to compute entries of matrices P and Q as small algebraic branching programs, and that can be done using the result. Second step is, once we have this linear matrix L, we use one of the important theorem from Cohn to reduce the problem of factorization of linear matrix to computation of non-trivial common invariant subspace of this matrix L. Then once we have such a reduction, we can use Ronai's algorithm to compute non-trivial common invariant subspace, and thereby we can compute the factorization of matrix L. At this stage, we have factorization of L, and then using basic linear algebra, we figure out the atomic factorization of F. We call this algorithm as factor extraction algorithm. So there are some key challenges we face while executing this broad plan. So first thing is to apply Cohn's theorem. We need to ensure that linear matrix L satisfies certain property called as monicity. In fact, we need to prove one-sided version of Cohn's theorem, which works with weaker assumption of right monicity, and this is in connection with final factor extraction algorithm, which we will see later. Second, by monicity, what we mean is, suppose L is a linear matrix A0 plus A1 x1 so on up to An xn. It is called as right monic if we stack up these matrices A1 to An in row-wise fashion. The resulting matrix has full row rank. And symmetrically, it is called as left monic if we stack up these matrices in column-wise fashion. The resulting matrix has a full column rank. And L is called as monic if it is both left and right monic. So we give an algorithm based on linear algebra, and which is similar to Gaussian elimination, to transform given linear matrix L to left monic or right monic or even monic matrix. Second challenge we face is to connect the problem of common invariant subspace computation with our problem of linear matrix factorization. We need to ensure that linear matrix L evaluates to an invertible matrix on all zero input, as we will see in the next slide. But of course, this is not always the case. So to get around this difficulty, we work with matrix blowups. So by matrix blowup, we simply mean we look at variables of capital L and we substitute suitable linear matrices for the variables, which leads to a larger matrix L prime, and which has property that if we evaluate it on all zero input, it evaluates to an invertible matrix. So though this takes care of the earlier problem, it gives rise to a new problem. So we will have factorization of L prime, but then our final goal is to extract factorization of L. So to do that, we need to crucially use a technical lemma from HKV20. So now let's see an important connection between matrix factorization and invariant subspace computation. So let C be a full monic linear matrix whose constant term is identity. Then C is not an atom if and only if under some suitable basis change, we can transform C to the block form shown. The form we discussed, which has the top right block, non-trivial top right block of zeros, where this matrix A is R cross R full monic linear matrix, and B is S cross S monic linear matrix. So we clearly see that if we have such a transformation with basis change with respect to matrix S, clearly we get a factorization of C as shown. And this factorization is non-trivial because these matrices AI and IB, we can see that they must be non-units. And reason for this is we know that A and B are monic, and monicity implies that they are non-units. It's not difficult to prove that. So essentially, we get a non-trivial factorization of C if we have common invariant subspace. And note that A and B again satisfy both the requirements. They are full and monic. So we can recursively expand out these two matrices further and get whole factorization of C. So at this stage, we have factorized linear matrix L into atoms. Our goal is to factorize polynomial f. So let's look at the equation fo plus id minus 1 is equal to p times c times d, where p is the upper triangular matrix with all ones diagonal, c is a full linear non-unit, where c is in fact the first factor of capital L, and d is product of rest of the factors with q. So our factor extraction algorithm is based on an algorithm for something called as matrix relation trivialization. So let A and B be two polynomial matrices which are possibly rectangular and which satisfy the relation AB equal to 0. We say that the relation is trivialized by unit n if for every index I, either ith column of an is all 0 or ith row of n inverse b is all 0. So what we do is we give an efficient algorithm to trivialize the matrix relation C prime V equal to 0, where C prime is some linear matrix and V is a column matrix with polynomial entries. And by efficient algorithm, we mean we give an ABP for if we efficiently compute small ABPs for entries of n and n inverse. Suppose C prime is the matrix obtained by dropping first row of capital C, and V is suppose first column of capital D. Then due to upper triangular nature of P, we get this relation C prime V equal to 0. Then using the trivialization matrix N, we can extract out non-trivial factors of F using simple linear algebra. The right monicity of L allows us to work with linear matrices C prime instead of general polynomial matrices. And a slight generalization of this procedure, if applied iteratively, we get entire factorization of F into irreducibles. So to summarize, we have given an efficient algorithm to factorize non-commutative polynomials given by formula, and irreducible factors are given by small ABPs. The algorithm works efficiently in case of finite fields. For small finite fields, we need to do a little more work, but it can be handled using standard technique of regular representations for elements in extension field. In a follow-up work, we have also extended our techniques to factorize matrix polynomials. Now, the common invariant subspace problem, which we have seen over rational, it turns out that the problem is as hard as factorization of square-free integers due to result of Friedel and Ronet. So clearly, our approach doesn't give an efficient algorithm in case of rationals, and we would need some new non-trivial idea. And we leave this as an interesting open problem. Secondly, instead of presenting polynomial f as a arithmetic formula, if we use other representations like ABP or arithmetic circuits, what is the complexity of the problem? Here it appears that the computation of Higman linearization itself seems a bottleneck. Thank you.